Okay, it looks like we're live. Okay, good. Hi everyone. Thanks very much everyone for coming. So today is our A-level physics session on projectile motion. So I'll be going through a session. The session will be split into two parts as usual, and at the end of each part, we will do a few exam questions to see how we're getting on. Also, feel free to ask me questions at any point while I'm going through things. If there's anything you're confused about, anything you want me to repeat, just let me know. And as long as I have time, I will make sure to try and answer you. I also might ask you questions along the way. And that's just to kind of make sure that you're all following and again, give me a chance to see if there's anything I think I should re-explain. Okay, good. So hopefully you can see the slides as well. In fact, I can see you can, so that's great. Good. So we'll just give ourselves an extra half a minute to let people come in. And then we'll get on with today's session. So as I said, today's session is on projectile motion. This is a really nice topic. It's what can we say? Well, it's about Newton's laws, but it introduces a new key set of techniques in dealing with Newton's laws, specifically to do with the fact that it's kind of two-dimensional motion. We're going to be dealing with things that are moving horizontally, that is left and right, but also things that are moving up and down, that is vertically. Okay, so let's take a look. I think we're in a good position to get going, so I'm just going to smash into the session. Yeah, okay, great. So like I said, just let me know if you have any questions. We have one issue. There we go. Good. Okay, so projectile motion. Just a quick bit about me and who we are. So this is from Snap Revise, and I personally am Matt Wilson. I'm the lead physics teacher here at Snap Revise. I was a physics PhD student at Oxford University. I've actually moved on, and I am a A-level physics tutor, or I have been at least for the last 7 years. So it's just a little bit of background about me. And now let's get to the important bit. Let's go through today's objectives. So today we're going to try and do three things. We're going to try and understand the concept of free fall. We're going to describe objects moving under free fall using the acceleration due to gravity g, and we're going to introduce this number g and explain what its relevance is. And we're going to solve, this was the bit I was mentioning before, this is a key bit today. We're going to solve 2D, that is two-dimensional projectile motion. So projectile is essentially for us something that moves in 2 dimensions. It moves up and down whilst also moving left and right. Classic examples would be something like throwing a ball. You never throw a ball completely horizontally. It always eventually hits the ground. Or firing a cannon, throwing a dart. These kinds of things are all projectiles. And of course, there are plenty more. Okay, even me jumping forward, that's a projectile. Okay, so there are going to be some things, some really, really key bits of information that we're going to want to know about today. Like I said, we're doing Newton's laws, we're doing motion, we're doing what's going to be basically the Suvat equations, but we're bringing them into 2 dimensions. So first of all, we need to introduce the Suvat equations. And secondly, we need to introduce vectors because those are going to be the things that let us use Suvat in more than one dimension at a time. Okay, so let's start by trying to recall the Suvat equations. I'll start writing them in, but feel free to write in any also that you know at the same time. Okay, great. Just 1 second. Okay, good. So the Suvat equations, I'm going to start with the equation for V, which says that V, my apologies, we just had a pen malfunction. So I'll be 1 second. This gives people in the chat a chance to write in the Suvat equations before I can. Okay, so feel free to race me to them. Okay, my apologies. We will be running again in a second. We have just had a quick technical issue, so I'm just going to deal with that now. Hi everyone. I'm afraid we are having an issue with my pen right now. That's really unfortunate. The stream's going to keep running, but I'm just going to have to go in and out of my computer again. So I'll be back any moment. And this still gives you plenty of time to write down those Suvat equations. Okay, everyone, I believe we're back. My apologies for that. Hopefully you can all hear me again. Do you just say straight away if you can't? Okay, it looks like we are indeed definitely back. Okay, this is great. This means we're finally ready to go through those Suvat equations. So, okay, our first equation says what? Our first equation says that the velocity at some time is going to be equal to the initial velocity plus the acceleration times the time elapsed between the point at which we had this initial velocity and the point at which we had this final velocity. Okay, so maybe let's establish some terms here. Let's imagine I have something that's moving through the air. There's some initial point. Let's call it this, initial. And there's some final point it reaches. Let's call it final. And we use u for the velocity that it had at the start, and we have v for the velocity it had at the end. We use t for the time it took to get from the initial to the final point, and we use s for the distance or the displacement between the final and the initial and final points. Okay, good. So those are the key things we need to know to understand the Suvat equations, but we have plenty more of these equations to write down. So there's the equation for the displacement, which says the displacement is equal to the velocity, the sum of the two velocities divided by 2 times the time. And you can think of this thing here as essentially being like an average velocity. Average velocity. So what this equation is really saying is that the displacement is given by the average velocity times the time. This is a very reasonable equation. Okay, a couple more, which are maybe a bit less intuitive. There's S equals ut plus a half at squared. Now, that may not be the most intuitive one, but it is the one that I think gets used the most. So it's definitely worth committing that one to memory. And then there's this one, which is, I think, maybe the hardest one to remember. V squared equals u squared plus 2as. At least I used to always forget it. Good. Okay. So those are the main equations that we're going to use to deal with objects moving around on the Earth. And there's a key assumption going on in the background of all of this stuff. And that key assumption is we assume that acceleration is constant. We can see that we're making this the assumption in our equations because there's just one mention of A. For velocity, there's an initial and a final. So velocity is allowed to change. But acceleration is just one number. There's never a change in an acceleration. There's never an initial and a final. There's just one number, the acceleration. Therefore, these equations to work, to be useful, it has to be the case that you're in a situation where you can assume you have a constant acceleration. Okay, good. We sometimes call this a uniform acceleration as well. Okay, so that's all about the motion in a uniform gravitational field. That is motion where we have constant acceleration. Now we need to deal with this two-dimensional thing. We need to be able to deal with horizontal motion and with vertical motion. Okay, so we're going to do that by resolving vectors. The idea is that if we look at some of the quantities in our equations up here, they're really vectors. We've got S, which is the displacement. And that's a vector. We've got V and U. Those are velocities. So they're vectors. And we've got the acceleration, which whilst constant is still a vector. Acceleration. So what this means is we can pick any direction we like, find a component of each of our vectors, S, U, V, and A, in that direction, and then the Suvat equations will hold in that direction. What this usually means practically is that we solve two Suvat problems. We solve horizontal Suvat equations and vertical Suvat equations. Okay, so for instance, let's imagine I have a displacement vector here, S, and I want to use Suvat in the horizontal direction. Then what I'll need to know is, for instance, this angle here, assuming this is a right angle, and then I'll know that this distance down here is going to be S cos theta. Similarly, if I want to use vertical Suvat, I'll have to find this vertical displacement, and that will be S times sine of theta. And when you want to do proper vertical and horizontal Suvat, you just need to do this for every quantity. And that's what a lot of today is going to be about. Okay, good. So here's the spec points that we're going to be going through today. As I said, if you have any questions, just let me know in the chat. Okay, good. Okay, this was the spec points for AQA. There's the spec points for OCR. And there's the spec points for EdXL. Okay, so before we start doing too much on two-dimensional motion, we're going to introduce the concept of free fall. And let's just go ahead. and go straight into it. The idea is essentially that we're going to be discussing the motion of objects, which we have just let go of and we have let fall in the field, in the gravitational field. Now know things that we know that things will speed up, they will accelerate when we let go of them. When I let go of a ball, it's moving at no velocity and then it speeds up towards the ground. So that's fine. What is surprising though, is that if it were not for evidence, if it were not for air resistance, then every object would fall towards the Earth at the same rate. Okay, so this is often phrased in terms of a hypothetical experiment of Galileo. I'm not sure if Galileo actually did this experiment or if it was just a hypothetical one, but let's imagine that they did. So let's imagine Galilei dropped two balls of different masses from the Leaning Tower of Pisa. The idea is to show exactly the point I just made, that they both would hit the ground at the same time. Now, this doesn't quite match on with our intuitions. Our intuitions tell us that if we drop heavier objects, they will fall faster. For instance, if I drop a bowling ball, I would expect that to hit the ground sooner than a piece of paper that I dropped. But it turns out that is all to do with air resistance, and that's something that we're not going to be taking into account for now. If there were no air, then this would really, really be true. Okay, so in the absence of air resistance, mass does not affect the rate at which an object falls under gravity. Falls under gravity. Good. Okay, so there's a really important principle, and there's another way you could see this. You could also imagine doing a more tractable experiment, something you could actually do in the lab. We can't all go up the Tower of Pisa and test this principle. And the reason you might wonder, why can't I just test this principle by holding these objects up at my height? And the reason for that is they would hit the ground too fast. It would be too hard for me to tell unless I had really, 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 really good sensors. If I drop things from a really, really large height, then the difference will probably magnify over time, and I'll actually be able to see the difference in the times at which two objects hit the floor. On the other hand, we can slow this whole thing down if we just make things roll along slopes instead. So you could imagine letting a ball fall down a slope or roll down a slope instead. And again, this would show that balls of different masses reach the bottom at the same time. On the other hand, there's an additional thing to point out here, something I didn't talk about too much yet. The ball will accelerate. The ball will move faster at the lower points of the slope than at the higher points of the slope. So let's write that down as well. The ball moves faster at the bottom of the slope than the top. Good. Okay, perfect. So this is all we need to know about projectile motion, well, free fall intuitively. And so now we're ready for the actual definition. So we say that an object is in free fall if it is only accelerating under gravity. Okay. This means, by the way, that its acceleration is constant. And it's not just any constant. We know what number it is. It's 9.81 meters per second squared. So that's the exact number that it actually is. Okay, now we have a word for objects which are in free fall, including those balls that would have been dropped off of the top of the Leaning Tower of Pisa. Those objects are all called projectiles. So this is an important point. An object doesn't have to be fired for it to be a projectile. It just has to be under free fall. Okay, so the good thing is, if we're in free fall, that is exactly the kind of situation in which we can use the Suvat equations. Why is that? Why can we use Suvat equations? Well, we've just said that the acceleration of an object in free fall is constant, and that's the key thing we need to use Suvat. Let's have a go at looking at an example of an object in free fall and using the Suvat equations to describe its motion. So here we're told that a ball is thrown upwards with a speed of 5 meters per second. For us to calculate the time for it to return to its starting position. Okay, so let's write down all of our key quantities, S, U, V, A, T. Now let's see, we're told an initial velocity of 5 meters per second. We're asked to calculate the time taken to reach a starting position. Well, let's ask ourselves, what is our displacement if we return to our starting position? But if we start somewhere and we return to that place, our overall displacement is actually 0. So they're asking us to find the time at which the displacement is 0 meters. Okay, we've not been told the final velocity, but we do know the acceleration. And an important thing to ask yourself here is whether you think the number I put here should be 9.81 or minus 9.81 meters per second squared. So which one is it? That's really worth thinking about, checking if you understand this. Now, you might want to answer that gravity points down and usually positive is upwards. Therefore, I should take gravity to be negative. And that's something I almost agree with. However, really what matters is that I chose a convention when I chose the side of this velocity. We were told that the ball was thrown upwards with a speed of 5 meters per second, and I called that a +5 velocity. Therefore, it was me in this question already who had chosen to treat the upwards direction as positive. Therefore, indeed, the acceleration being downwards will be minus 9.81 meters per second. Okay, good. So now we're ready to answer the question. And as I said, the classic equation to use for many of these problems is S equals ut plus a half at squared. Why? Because often we don't know the final velocity. That's usually the hardest thing to know, I guess. Okay, good. So we want to know the time, so let's rearrange for t. We've got 0 here equals t times u plus 1 over 2a times t. And so we have two solutions to this equation. Either t equals 0. Well, of course, at time t equals 0, our displacement would be 0. But that's not the answer we're looking for. We're looking for some other time. So the equation we have to solve is u plus 1 over 2at equals 0, which implies in turn that the time is equal to minus u over, let's get this right, minus u times 2 over the acceleration, which implies that our time is equal to minus 5 times 2 over minus 9.81. And if we chuck that in a calculator, we'll get 1.02 seconds. And it's always a good sign when the time comes out positive like this. This is a sign that I probably did set up all my signs in the right direction to begin with. Okay, great. Hopefully this is making sense. How confident is everyone feeling? How are people getting on with this so far? Okay, well, I don't see any questions in the chat, so I'll go straight on to do some exam questions. If there are any questions, just let me know in the chat. Okay, so this is a really good exam question. We're told that a dartboard is thrown horizontally. Sorry, a dart is thrown horizontally at a speed of 8 meters per second towards the center of a dartboard that is 2 meters away. Okay, there's going to be a big paragraph of information here, which is a warning sign that I should probably start drawing a picture. So we have a dart. Okay, yes. Thrown horizontally at a speed of 8 meters per second towards the center of a dartboard. So here's a dartboard, and the center is here. Okay. At the same instant that the dart is released, the support holding the dartboard fails and the dartboard falls freely. Okay, so the dartboard is under free fall from gravity. Dart hits the dartboard in the center before they both reach the ground. Okay, so at some later time, let's cordon off and find some later time. Both things have fallen down. And they're saying that the dart hits the dartboard in the center. So we end up in this situation. Okay, we're asked to state and explain the motion of the dart and the dartboard while the dart is in flight. And so it's worth asking what it is that they're actually asking us to explain here. Okay, well, there's 4 marks. So we can probably talk about the horizontal motion and the vertical motion. We state what happens in each case, and then we explain what happens in each case. Okay, and then we should take a look at this problem. Why is it that actually the dart hits the center of the dartboard? After all, the dartboard fell. So surely the dart would miss the dartboard. Well, no, the dart was initially aimed horizontally. Therefore, it is also starting from a vertical velocity of 0, feeling the same acceleration downwards. Remember, every object falls at the same rate, and that's what they want us to talk about here. Okay, so you may be awarded additional marks for quality of written communication. Let's have a go. So first of all, the dart and the dart board both accelerate at the same rate from a beginning vertical velocity of 0 meters per second. Okay. This means that at any point they will have fallen to the same vertical displacement. Same vertical displacement. Good. And maybe I should just do one more thing. I should mention the horizontal motion. The horizontal velocity of the dart remains constant since, I have to explain this as well, since the only acceleration is downwards. Now, this is slightly counter to our intuition. Our intuition is that dart would slow down in the horizontal direction too. And all that's happening there is that in the real world, we have air resistance, and air resistance is not being taken into account here. Okay, good. Okay, another question. In this question, we're shown figure 2.1, which shows an arrangement used in a laboratory to determine the acceleration g of free fall. Okay, good. So we're told that the steel ball is held at rest by an electromagnet, and when the electromagnet is switched off, the electronic timer is started and the ball falls. The timer is stopped when the ball opens the trapdoor. Okay, so here's the ball. It's going to fall. It's going to eventually crash into the trapdoor, making it open. The timer is stopped when the ball opens the trapdoor, and the distance between the bottom of the ball and the top of the trapdoor is 0.6 meters, and that's all in the diagram. Great. The timer records this time of fall. Show that the value of acceleration g for the free fall obtained in this experiment is 9.47 meters per second squared. Okay, well, this is going to be a classic Suvat equation question. We're going to assume constant acceleration. And then let's look at what we've got here. Do we know the displacement? Yes, we know the displacement is 0.6. Now notice, what direction have I chosen to be positive here? We began at the top, we finished at the bottom. Therefore, I have chosen here for the displacement for positive to be downwards. This is important for when I come to declaring what the acceleration is going to be in my Suvat equations. Now, this thing is dropped from rest. So the initial velocity is 0. The final velocity is usually hard to know, and we don't know it here. The time is 0.356 seconds. Now we're going to try and find the acceleration. Sorry, we're not actually going to declare the acceleration. If I did declare it, it would be 9 plus 9.81. But actually, the acceleration is the thing we're being asked to find here. But we're going to find that it's positive, even though it's downwards. And that's because my convention in the displacement here was to make downwards be positive. Okay, good. So let's go ahead. And the classic thing is to use S equals ut plus half at squared because we don't know the final velocity. So we want the equation that doesn't include v. Good. Okay. The initial velocity is 0, so we can get rid of this term. And we just find that the acceleration is equal to 2 times s over t squared, which is 2 times 0.6 divided by 0.356 all squared. And if you check that in a calculator, you get 9.468501, etc., meters per second squared, which is indeed roughly equal to 9.47 meters per second squared, which is exactly the value they wanted from us. So perfect, that's great. Okay, but it's a bit odd. We usually say that acceleration due to gravity is 9.81 meters per second squared. So what have we missed here? Well, they want us to know. They ask us to state one reason why the experimental value that's gotten here, 9.47, is less than 9.81. So remember, we got 9.47, which is strictly less. Well, the classic answer is in this experiment, the ball will also feel an upward acceleration due to air resistance. Okay, good. In the next part of the question, on figure 2.2, we are asked to sketch a graph to show the variation of the vertical distance s fallen by the ball with time t. Okay. So let's assume that we start up here at 0.6, and I want to start up there because my displacement was downwards over time. Okay, so I want to draw it. And the key thing to ask ourselves is whether we think the shape is going to be a curve like this. Eventually, we know we reach zero. Maybe a straight line like this, or maybe a curve like this. Those are the three natural options. And of these options, the correct one is this one here. So why is that? Well, if we look at this graph, we see that we have a flat-ish gradient at the start and a steep gradient later. That means we have a large velocity here and a small velocity here. And that's exactly what you'd expect for something that you've dropped that is accelerating. It should be faster at later times. So that's why it curves like this and not like this. Okay, good. Hopefully that is making sense. Okay, so we're finally ready to talk about projectile motion. And this is going to be the bit where we start doing some two-dimensional maths. Okay, so in other words, we have Suvat, which we understand, and now we're going to do Suvat with vectors. And the key principle here is the following. Suvat, which is a system of equations that you can use, is true. In other words, you can use it in A, the horizontal direction, and B, in the vertical direction. Vertical directions. It's true for both at the same time. So you can look at all the horizontal quantities, you Suvat on those. Often you'll use that to figure out a time which is shared between the horizontal and the vertical stuff. And then use that time to figure out some vertical quantity. So sometimes you have to really use both systems of equations together, or one before the other usually. And we're going to see an example of that now. So let's imagine that we have this situation here. What is this situation? This is a situation in which we have a projectile which is fired at an angle. This is 4 meters per second, and it's fired at an angle of 30 degrees. Okay, good. Our goal is going to be to find out h. That is, we're going to be trying to find out the height from which this projectile was fired. And we're told something, but the thing we're told is super inconvenient. The piece of data we have is in the horizontal direction. So how do we go from this horizontal piece of data to the vertical piece of information we want to find? Well, the connection between those horizontal and vertical equations is the time. The time between the initial point and the final point is the same, whether you're looking at all the vertical quantities or the horizontal quantities. And that's going to be the key idea. Okay, so we're going to start with horizontal motion because we've been told some horizontal stuff. Okay, so what can we say? Well, first of all, recall we've got this 4 meters per second here. If we're going to want to deal with horizontal, we're going to need to split this into components. Remembering this is 30, then our initial horizontal velocity is going to be 4 cos 30. Alternatively, our initial vertical velocity will be 4 sine 30, and that will be handy on the next page. Okay, so let's see. For the horizontal motion, we could look at S, U, V, A, and T. But, and this is something worth asking yourself, so feel free to pause here. What is the acceleration in the horizontal direction? If it was vertical, we'd know that it was 9.81. It would be the acceleration due to gravity. But what about the horizontal acceleration? It's moving horizontally. We fired it horizontally. Is it accelerating horizontally? And in the absence of air resistance, the answer here is always no. So the acceleration is 0. Okay, our goal is to find the time. The time connects horizontal to vertical. That's the principle. Do we know the vertical displacement? Yes, it's free. Do we know the final velocity? Well, actually, we do. We know the initial velocity is 4 cos 30, but since the acceleration is 0, the final velocity is also 4 cos 30. Anyway, it turns out that since there's no acceleration, this is just a speed equals distance over time problem. Indeed, if we look at s equals ut plus a half at squared, if a is 0, we can get rid of that, and it just says distance equals speed times time. We want time, so that's going to be speed over distance, which is going to be 3 meters. Sorry, distance over speed, which is going to be 3 meters over 4 cos 30. Check that in a calculator and you'll get 0.866 seconds. Okay, perfect. What time have we figured out there? We have figured out the time that it would take to get from this point here, let's call it the initial point, to this point here. Let's call it the final point, I guess. Okay, so now we figured out the time between these 2 points. Now we can use that time in a vertical Suvat question, vertical Suvat equation to figure out this h. Okay, great. Let's do that. So to deal with the vertical motion of the projectile, recall that the acceleration is equal to g, which is equal to 9.81 meters per second squared. Okay, good. So we know the time, we just calculated it, is 0.866 seconds. 6 recurring, I believe. Okay, we already calculated the initial vertical velocity. It was 4 sine 60. Now, if I've called this 4 sine 60, ask yourself, well, which direction have I declared to be positive? Well, I've called that upwards quantity a plane 4 sine 60. So the acceleration, a downwards quantity, should be minus 8.1 here. And the displacement is something we want to know. Notice that we started here, finished here. So our displacement was downwards, which means it's negative h, because upwards is positive for this question today. That's the convention I've chosen. Okay, so again, the final velocity is hard to know. We don't want to think about that. So we use s equals ut plus a half at squared. We want to know s, so this is minus h equals, let's see, initial velocity is 4 sine 60 times the time, which is 0.866 plus 1/2 times minus 9.81 times t squared, 0.866 squared. If you chuck this in a calculator, you'll find that h is in fact equal to 1.9466, etc. In other words, it's equal to 1.9 meters. H equals 1.9 meters. Perfect. Okay, so we solved the question. And recall, the key idea is that we had to use one direction of Suvat first to figure out the time so that we could then use the other direction of Suvat. Good. Okay, so hopefully that's making sense. Do let me know if there's any questions. And I'm going to go on just because we lost time slightly and head on to the last exam questions. But still in the chat, let me know if you have any questions. Okay, so in this question, we're told about figure 3. And figure 3 shows the path of a ball thrown horizontally from the top of a tower of height 24 meters, which is surrounded by ground level. Okay, we're asked to use 2 labeled arrows to show on figure 3 the direction of the velocity v and the acceleration a of the ball when it's at point P. This is a fantastic conceptual question. So let's start with the acceleration. And the path that's been drawn here is really misleading. They're trying to get you to make a mistake. They're trying to get you to say that, well, it looks like the acceleration is in this direction. That's where the motion is. Now, this is false. The only acceleration in this diagram is the acceleration due to gravity. And the acceleration due to gravity is always downwards. So ignore the path when you're thinking about acceleration. The acceleration is the direction in which the motion is changing, not the direction in which the motion is going. Okay. On the other hand, the velocity simply points in the direction of motion. So in fact, this other arrow that we drew is perfect for the velocity, just not for the acceleration. Okay, good. Next question. We're asked to calculate the time taken from when the ball is thrown to when it first hits the ground. And we're allowed to assume air resistance is negligible. And we should recall that in this question, we were told that we begin at a height of 24 meters. Interestingly, we were not told anything else. Okay, so let's use Suvat as usual. We're being asked to find the time. What do we know? We know the acceleration. We know our displacement was downwards. So let's call the displacement 24. And then since we've chosen downwards to be positive, the acceleration is just plus 9.81. Final velocity, as usual, we don't know it. Initial velocity, we were told that the ball was thrown horizontally. This is really important. That's hidden maths in words. So be aware of this. The ball was thrown horizontally. In other words, the initial vertical velocity is 0. The only velocity it has, the only component is in the vertical direction. Okay, good. So this initial velocity is 0, and then we're in a really good position. We can use Suvat. We have S equals, we have S equals ut plus 1/2 at squared. U is 0. And we're being asked to find the time. So let's rearrange for time. Time here equals 2 times S over A. And we've got to take the square root. Chuck that in a calculator. We've got 2 times 24 over 9.81. And in a calculator, that gives us 2.21200, 220, etc., which simply gives us 2.2 to 2 significant figures. Okay, good. Next question. In 4B, we're told that the ball hits the ground 27 meters from the base of the tower. We're asked to calculate the speed at which the ball is thrown. Okay, good. So this is let's see, 27 meters from the base. This is a horizontal piece of information now, but we just figured out the time. So that's going to help us with horizontal Suvat. So they want the speed. Well, okay, if we look, the initial speed, that's the thing we want to know. The displacement is 27. The acceleration is 0 because it's horizontal. The acceleration in the horizontal direction is 0. That's what we saw in that previous part of the question where we actually drew the acceleration. See, we drew the acceleration downwards, meaning that the horizontal acceleration is 0. Okay, so we're using that here. The horizontal acceleration is 0. And we know the time between being projected and landing was here, 2.2 seconds, or in more generally 2.212, etc. from over here. Okay, good. Well, this is just speed equals distance divided by time. And we're being asked to find the speed. So the speed is equal to distance divided by time because the acceleration is 0. In which case we have 27 divided by 2.212, etc. We can chuck that in a calculator and we'll find 12.206. In other words, we'll get 12 meters per second. Okay, good. Hopefully that is making sense. So we have one more question, and it's a really nice one. Okay, hi. Okay, in question B, figure 1.1 shows the path of a ball that is thrown from point A to point B. The ball reaches its maximum height at point H. The ball is thrown with an initial velocity of 25 meters per second at 60 degrees to the horizontal, and all that information is in the diagram, so that's perfect. And we can assume there's no resistance, which is just code for you can use Suvat stress-free. Okay, question 1. We're asked to show that the vertical component of the initial velocity is 21.7 meters per second. Well, okay. We start with our vector. We want to split it into horizontal and vertical parts. We know this angle is 60. We know this side here is 25. This is going to be 25 sine 60. If you chuck that in a calculator, you'll get 21.6506, which is indeed roughly 21.7 to 3 significant figures. And that's meters per second because it's a speed. Good, okay. Part 2, we're asked to calculate the time taken for the ball to reach point H. That's a really nice question, and it's going to require us to use a new technique that we actually haven't used yet today. So let's look at the Suvat quantities S, U, V, A, and T. We want to know the time. We know the acceleration is minus 9.81. Yeah, I'm afraid today is just projectile motion, but I will take that into account for when we decide what to do in future sessions. But yeah, today is just projectile motion, I'm afraid. Good, okay. So we have 9.81 here. Let's see, the initial velocity, yes, we just found that out. It's 21.7 meters per second. The displacement, we have no idea. So this is kind of an odd situation. This is one where we have to figure out this thing to make any progress. But we can figure this out because H is the highest point in the motion of this projectile. And there's a new rule here that we should remember, which says that at the highest point, no problem. At the highest point, the vertical velocity is 0. This is super important. And it makes sense. Beforehand, we're moving upwards. So our vertical velocity is upwards. Afterwards, we're moving downwards. So our vertical velocity is downwards. Therefore, right in the middle of those, our vertical velocity must be equal to 0. Exactly right. The velocity is equal to 0. Okay, good. So now we're in a good position to answer this question because we know this is 0. So we can use V equals U plus AT. That's another one of our Suvat equations. We want to rearrange for T, which gives us V minus U over A. This makes sense. This is just kind of the definition of acceleration. Acceleration is change in velocity over time. So time is change in velocity over acceleration. Okay, good. This implies that T is equal to minus, did I get this right? Yeah, this is upwards. So minus, yeah, good. The signs are going to work out. 21.7 over minus 9.81. Chuck that in a calculator and you'll get 2.20699, etc. And yeah, you're absolutely right. Good. That's 2.21 to 3 significant figures seconds. Okay, notice that the quantities I gave are in 3 significant figures. That's why I'm also giving my answer to 3 significant figures. Okay, hey there. So we have one more question left. We're asked to calculate the displacement from A to B. Okay, so there's a few ways of doing this. The way I think I want to do this is to try and figure out the time. And this is another one of those classic questions where we're going to need to use vertical Suvat first to figure out stuff that we can then use in horizontal Suvat. Okay, good. Now, in fact, we have at our disposal a trick. So something I could do is do vertical Suvat from scratch. I could say, okay, let me write down in the vertical direction S, U, V, A, and T. The displacement would be 0 because I'd be going from this point to this point, which vertically is just the same height. Yeah, so I'm going to use a parabola trick, but I want to explain how you could have done it otherwise anyway. I'd be trying to figure out the time. The acceleration I'd know. The initial velocity I'd know. And this would be plenty to figure out the time. However, we just figured out the time here to get halfway. We just figured out the time it takes to get from here up to this point here. And whenever you figured out that in the Suvat question, whenever you figured out the time taken to get to the top, you can just double the time to find the time taken to get back to the bottom again. In other words, this path here takes exactly the same time that this path here does. Yeah, there you go. So in fact, since we know the time getting to halfway was, so now a half of our time is the time to the top, which is 2.20699, etc. We in fact know that the time, good, we in fact know that the time is around 4.41399, etc. Okay, that's great. Now we can calculate the displacement. Why? Because we know the horizontal velocity. We have it here, in fact. The horizontal velocity is 25 cos 60. So altogether, we have that the displacement equals 25 cos 60 times our time of 4.41399, etc. Chuck that in a calculator, and you will get around 55, so roughly 55.2 meters to 3 significant figures. And there you go, that completes the last question. So remember, the key idea here in all of these questions was that we know Suvat, which we can use whenever the acceleration is constant, and we can split our problems into a vertical problem and a horizontal, a vertical problem and a horizontal problem, and we can solve those separately. And the thing that links those two equations is the time. Okay, good. So after this session, you should now understand the concept of free fall. That's fall in a constant gravitational field. You should be able to describe objects under free fall using acceleration due to gravity. In other words, you should be able to describe their motion and figure out their motion using the Suvat equations. And furthermore, you should be able to combine vector methods with Suvat methods to solve these projectile problems for objects which are moving in 2 dimensions in a constant acceleration. Good. So hopefully that's making sense. Does anyone have any questions? Apologies again for the tech issues at the start. Luckily, after one reboot, it looked like everything went back to normal. So that's great. But yeah, so does anyone have any more questions? I can see there's something in the chat actually. Couldn't we use parabola and calculate the maximum height? So I think you're maybe suggesting the kind of thing that we did, in fact, which was we used the time taken to get to the maximum height, and then we just doubled it to find the time taken to get to the end. I'm actually not sure what the next topic is, but it should be on the Snap Revise. What do I call it? If you go on the Snap Revise channel, all the live streams are lined up. So let's see if there's a new one lined up. No, there's no new one lined up yet. So yeah, I don't know what the next one will be yet, I'm afraid. Sorry. Yes, great. Yes, I thought that was what you're saying. Good. Were there any other questions? For A-level physics, you won't really need derivatives, no. It's helpful to know about them. It means you'll see some things quicker than if you hadn't seen and used derivatives before, but you don't need them. Helpful, but yeah, we didn't need them here. I'm guessing in A-level maths, you probably will need them. But here, no need. Okay, I see. Okay, well, in that case, this kind of thing is useful, I guess. Any 3D problem? The answer is yes, but luckily not in your physics or I guess probably your maths exam at A level. If you want to deal with 3 dimensions, it's often easier to use a thing called spherical coordinates. But that's something I think you're more likely to do more of at university. It might come up a bit in like A level mechanics in the maths side, but I'm not sure. I actually can't remember. It's a little while since I did maths mechanics. No, I think spherical coordinates is university. Yeah. Yeah. So you do end up doing it actually. I mean, actually, if you want to study general relativity, you have to treat time as another dimension and do weird 4D things, but that's a whole other story. Okay, so I think we've run over there, so it's probably a good time for me to sign off. I hope that that was useful for everyone, and I look forward to seeing you at the next session. Okay, well done everyone for going along, and yeah, catch you next time. Bye.